This is Gyroscopic Precession Part 6. At the end of Part 5 we were looking at the propeller of the steel stork. It's a 60 by 30, 3.5 pound wooden propeller built by Tennessee Propellers. Okay, the website's supercoolprops.com and another one or two. They say the radius of gyration of a propeller is generally about 55% of the way from the center to the tip, 55% of the radius. So, and on the steel stork it's a 60 by 30. That 60 means 60 inches diameter, that 30 means 30 inch pitch, so we take that 60 and divide it by 2 to get 30 inch radius. We multiply that by 0.55 to get 16.5 inches is our radius of gyration. K is the letter we use for that. But we're not going to use inches in our equation, we're going to use meters. So 16.5 times 2.54 centimeters per inch gives us 42 centimeters, which is 0.42 meters. Okay, remember that the radius of gyration is the radial distance from a given axis at which the mass of a body could be concentrated without altering the rotational inertia of the body about that axis. The moment of inertia equals mass times the radius of gyration. There we go. Moment of inertia equals mass times radius of gyration squared. Okay, so our propeller's moment of inertia is mass 1.6 kilograms. It's a 3.5 pound propeller at 2.2 pounds per kilogram. That gives you 1.6 kilograms times our radius of gyration, 0.42 meters squared. So we have 1.6 times 0.42 times 0.42 gives us 0.28. We have kilogram meters squared. That's the moment of inertia of our wooden propeller on the steel stork. Okay, the angular momentum of our propeller is equal to the moment of inertia times the angular velocity. We use the letter L for angular momentum. I is moment of inertia. Omega sub r is angular velocity, rotational angular velocity. In other words, the number of radians that a propeller is spinning around on its axis. Okay, the steel stork's propeller at full power spins at 2100 revolutions per minute. Okay, each revolution is 2 pi radians, so it's spinning 13,195 radians per minute. This is 220 radians per second. Divide that by 60 and you'll get 220 or somewhere close to that. So that's our that's our angular velocity that the propeller is spinning about its axis, the propeller shaft, 220 radians per second. Okay, if we do a power on stall with a propeller spinning at 2100 revolutions per minute and the nose of the airplane plummets 1 radian, 57 degrees in 1 second, then the resulting gyroscopic torque will be, let's see, uh-oh, I skipped something here. Okay, so let's get back to our angular momentum. Okay, our moment of inertia was 0.28 kilogram meter squared. Our angular velocity is 220 per second, so 0.28 kilogram meter squared times 220 per second equals 0.28 times 220 is going to be 61.6. We have kilogram meter squared per second. Okay, so now we can talk about our power on stall. If the propeller is spinning at 2100 RPM during a power on stall and the nose of the airplane plummets 1 radian or 57 degrees in 1 second, then the resulting gyroscopic torque, okay, that 1 radian per second, that would be our precession rate. Our resulting gyroscopic torque will be gyroscopic torque equals angular momentum times the precession rate. Notice this is omega sub p, not omega sub r. Omega r, that's the fast one. That's how fast the propeller is spinning around. Omega sub p is how fast you're changing the axis about which the propeller is rotating. In other words, the propeller shaft. You're aimed up in the sky and then you're aimed down toward the ground. So fortunately that's not near as fast as this is. You'd be in big trouble if it were. Okay, so gyroscopic torque equals angular momentum times the precession rate, which we are assuming is 1 radian per second. So gyroscopic torque will be angular momentum. We just figured that out, 61.6 kilogram meter squared per second, times our precession rate. The nose is falling 1 radian per second, so 1 per second. Multiply that times that, and we get 61.6 again. Of course, our units are a little different. We have kilogram meter squared per second squared now. Okay, this gyroscopic torque, which the propeller puts on the rest of the airplane, is 61.6 kilogram meter squared per second squared, which is 61.6 Newton. Let's see, Newton meters. Okay, because a Newton is a kilogram meter per second squared. So a kilogram meter squared per second squared would be a Newton meter. So, of course, we Americans, we think of torque in terms of foot-pounds. So how many foot-pounds is 61.6 Newton meters? Well, we know that we can turn our pounds, our newtons, into pounds by multiplying it by how many pounds equals how many newtons. 1 pound equals 4.45 newtons. So, and we know we have 3.28 feet per meter. So Newton meters times pounds per Newton gives us pound meters. Then pound meters times feet per meter gives us feet pounds, or foot pounds. So that divided by that multiplied times that gives you 45.4 foot-pounds. Okay, remember that the gyroscopic torque that the propeller is exerting on the airplane is not the same as the torque that the engine is putting on the propeller. The propeller of the steel stork, as viewed from behind the airplane, spins counterclockwise. This makes the airplane tend to roll clockwise. This little airplane can illustrate what we're talking about. The propeller of the steel stork, as viewed from behind the airplane, if you're looking this way, spins counterclockwise, so going around like that. Okay, this makes the airplane tend to roll clockwise. Okay, because anytime your engine is turning this thing that way, the engine wants to turn the rest of the airplane that way. Okay, the gyroscopic torque that the propeller would exert on the airplane as the nose of the airplane drops, okay, if we're spinning along counterclockwise and the nose just drops, that's just like pushing forward on there, so it'll go over that way. It'll make the nose tend to turn to the right. So as you can see, these two different types of torque, the torque on the propeller shaft, crankshaft, and the gyroscopic torque, they cause the airplane to rotate on two different axes. The engine driving the propeller torque causes the airplane to roll on its longitudinal axis. That's the axis that goes from the nose to the tail, so it causes it to do that. That's what the engine driving the propeller torque does. Okay, the gyroscopic torque causes the airplane to yaw on its vertical axis. In other words, turn to the right, the axis that goes straight up through the airplane. In order for the propeller to exert a gyroscopic torque that causes the airplane to yaw to the right, in other words, this propeller here is doing this, turning the airplane to the right, then the right side of the propeller shaft, so here's the propeller shaft, this is the steel stalk, it's a pusher, the propeller is behind the engine, there's the pulley, there's the propeller shaft. So the right side of the propeller shaft is going to be in tension because this propeller is trying to turn the airplane that way, and the left side of the shaft over here is going to be in compression. Okay, the steel stalk has a pusher prop, as I said, engine in front is going that way with the engine. Okay, if it were a tractor, the right side of the propeller shaft would be in compression and the left side would be in tension. So after 1/4200th of a minute, which is 1/70th of a second, which is the time it takes for this blade to go from this side over to this side, 1/2 of a revolution, it's turning 2100 revolutions per minute. So after 1/4200th of a minute, that's a half a revolution. Okay, the side of the propeller shaft that was in tension, here's a little blow up of it. This is the propeller shaft, this is the propeller. Well, the side over here that was in tension flips over to here and becomes in compression. And the side that was in compression over here, it's flipped back around over here, it's in tension after 1/4200th of a second. The engine driving the propeller torque causes shear stress in the propeller shaft. Let's look at these two dots here. I drew a couple of dots on the propeller shaft. Okay, the engine is turning this shaft and it's going counterclockwise, looking at it from behind. So this point is trying to go this way a little bit, and this one is resisting it, so it's kind of wanting to go that way. So you have a little shearing action because the engine is doing work turning this shaft round and round. Okay, this is while the axis is not being moved. I mean, the propeller's spinning around, but you're not doing this or this, any of that, just spinning around. You have that shear stress across there. Okay. The lesson to be learned here is that this propeller shaft is subjected to two different types of stress in two different directions. Let's look at the 2 points on the side of the propeller shaft. Okay, these two, let's draw them over here. Okay. So when this side is in tension, this side, whatever's on this side is always in tension. So this point is trying to pull away from this point. They're being pulled apart. When these 2 points are on this side of the propeller shaft, they're being compressed together, but yet they're still being sheared the whole time. So what we have is, here are 2 points. We have this point being sheared and wanting to go that way because of the engine turning the propeller shear stress in the drive shaft. We have it in tension, being pulled this way when it's on one side of the shaft. We have it in compression, being pulled that way when it's on the other side of the shaft. Those alternate back and forth. So we have 2 different directions of stress. So the stress in each direction that is allowed is determined by the stress in the other direction. So in part 7 we'll talk about our quarter circle graph, which is used to determine how much stress we are allowed when we have stress in 2 different directions.